Myself, Takaharu Suzuki, will present Holonavi, a study on user interface for assembly guidance system with mixed reality in a timbercraft of architecture, on behalf of all other members of Keio University SFC. This paper introduces ideas to use mixed reality technologies in craftsman's work of architecture. Among many techniques in architectural work, we choose Japanese traditional timber joinery kumiki as a model case of complicated architectural work. We found that people need a certain sense of 3D recognition and knowledge about the right order of assembly. That is what we can suggest for users with our MR guidance system named Holonavi, which can show appropriate information in 3D vision in real time. The aim of our research is to find useful knowledge about effective ways and sufficient information to guide users. As a conclusion, we found that guidance with MR technology gives users to have a recognition more effectively for taking right action when they are moving their viewpoint around the object and when they located in the range of reachable distance to the object. It is a first achievement for use of Holonavi to let people feel more fun to craft something by their hands aided by computer. One of the background of this study is the emergence of the mixed reality technology. The technology is much easier to use with new devices such as Microsoft HoloLens. Before our project in application of MR for general methodology of instruction in assembly, we did investigate and referred prior projects and studies that utilize those technologies for construction. Takenaka Corporation and Honeycomb Lab jointly developed an application which assists construction with HoloLens. By displaying information about component or mounting position in a real space, number of process of verification is shortened. MR is applied in those projects above, especially for process of construction work. MR enables us to do intricate design, so that could be helpful for traditional craftsmanship work, such as Japanese timber joinery. In traditional assembly work, the processes of construction are conveyed using oral communication. Then, the assembly technique itself was tacit knowledge of some specific craftsman, such as welder or shrine carpenter. However, those traditional techniques would be more general and be applied in unconventional ways through MR. Emerging tools like MR with computational modeling gives us new opportunity of craftsmanship with human data interaction, instead of replacement of human effort from construction. We started from researching Tsumiki, which is Japanese traditional timber construction system that requires complex process. Tsumiki is a suitable system for this research because it is a traditional, iconic, and important wooden joint system. In this paper, we examine Roppon Tsumiki, which is one of the simplest Tsumiki systems that consists of 6 timber components. However, this research aims not only to hand down the skills of wooden joint, but also to consider how to utilize that traditional timber technique. It is expected to be applied to innovative construction systems that combine wooden technique and digital technology. The assembly support system with MR enables not only to increase the number of components, but also to construct more complex architecture. These are the list of tasks which are necessary to be solved for the development of our MR guidance system named Holonavi, which guides construction of Tsumiki. First, construction in correct order. Second, assembly in correct direction. And third, selection of correct component. Firstly, in order to develop better interface for MR guidance, We started from an investigation in previous techniques in instruct assembly in graphical way such as printed manual. However, in many cases, it is difficult to let someone to be able to craft object in their hand properly only with oral instruction and 2D drawings. These skills are obtained by sufficient experience. Therefore, we analyzed paper manuals of assembly and explored how to convert them into three-dimensional information. Next, we created three-dimensional image of that information. Then, we let the research subject to experience it, to understand the contents and assess the three-dimensional manuals. The paper manual cannot specify the light component, light direction, and order. Therefore, to enable that in the 3D manual, we assign IDs to each component in order to let people pick up a component initially, with displaying only hologram of actual shape of it. Technical issue appeared in the first trial, where a Ruko marker was stuck on a target component and suggests next hologram. We found that it is better to fix the target component for the sake of assembly in a similar way as actual construction. The finding suggests that location-based AR can provide more stable condition of hologram without changing the display depending on the location of component. In addition, the research subjects can understand the output better because they were able to move around the component during assembly. As the second trial, we fixed a marker in a field of vision and fixed a component on the assembly environment. In the first trial, the research subject needed to use both of their hands to assemble. However, in this case, they became able to look at the hologram more stably. We applied Holonavi to the actual assembly. The results showed that Holonavi enables the assembly to be easy and correct. On the other hand, some points still have to be improved. Many people are unfamiliar with the interface of HoloLens, so the fact that they have to click a button when switching between steps takes a lot of time. In terms of work progress, if the subject himself or herself does not notice a mistake, the process proceeds to the next task. The problem may be solved by requiring a mechanism that allows the computer to evaluate the resulting shape each time. From the viewpoint of component selection, the subject spontaneously selects component by watching the movie animation. In this case, the correct part can be selected, but it depends on the subject's ability of the selection, so it might not be said that it is possible to provide suitable guidance. However, if we use Viewfolio, we can accurately capture objects. It is possible to search for the correct part using the computational simulation, and even if it is confusing part, it will be possible to search without errors. After experimental operation and feedback, we noticed there are more potential in the current system. Firstly, the current system in Tsumiki assembly is for single person, but it has a potential to create collaborative communication through the system with multiple works. Secondly, we understood that MR is more effective when dealing with large objects and causing physical movements rather than small objects in your hand. Thirdly, the system is able to help us not only to get a planned goal, but also to see goals through the interactive process when it is more integrated with computational model. We worked on SGB based on those possibilities we felt with Holonavi. In this system, we are experimenting with scaling up, multi-personalization, adaptation to human intervention, and so on. It is possible for a third person to recognize or grasp what another person figures out the workflow who works on this assembly. We can recognize how a worker can be physically affected by using MO by handling something with a physical sense of scale. In this system, by linking virtual and real to speed up try and error, we can more intuitively assemble blocks. Can we discover any other blocks intuitively? We can select a new block to be assembled from virtual suggestion. Can we make space based on the body? At first, we can position based on the body. Can we agree about contents of work? We can work together with multiple people. We use various sensors to measure the position and angle to extract digital data from the real world. By using these data, it is possible to display the next connectable block and to temporarily place or delete it. Therefore, anyone can assemble blocks and design while reconsidering. So next step of our research will investigate how effective the assembly work guidance is in the MR environment through experiments such as scaling up, multi-personalization, and adaptive for human intervention. Thank you for listening.